Welcome to the very last PowerPoint that you guys have to go through for Year 11 biology. I'm sure you'll be watching these for years and years to come. Just absolutely stoked about how fun Year 11 biology was. And we're going to finish up on a high and talk about something that I think is a very, very interesting topic in Year 11 biology, and that's all to do with pedigree charts and genetic testing. Very, very important and hot topic around the world, really. Very good meme. Your family tree must be a cactus because every member of it is a prick. All right, pause the video here and have a go at the 3 quick questions. We'll talk about these next lesson together. All right, so in the study design, we're talking about Unit 2, Area Study 2, Biology. So still that pedigree charts, genetic cross outcomes, genetic decision making. All right, we're finally going to go through that pedigree charts and patterns of inheritance area, including the 5 types of inheritance, which we talked about, which are autosomal dominant, autosomal recessive, X-linked, which can be recessive and it can also be dominant, all right, and then Y-linked traits, okay? And then also we're going to quickly talk about the nature and the uses of genetic testing for screening of embryos and adults and its social and ethical implications. All right, so let's go through the last point first. So the testing of an individual to determine the risk of a person being affected by an inherited disorder where a family history is present, and the genetic risk of offspring of known carriers of a genetic disorder. This is genetic testing and the reason why we do genetic testing. All right, genetic testing is conducted on adults or non-infants, like I like to call us. And there's examples of genetic testing such as Huntington's disease, testing women with family background of ovarian cancer. Okay, genetic screening, on the other hand, actually evaluates the degree of risk that a genetic disease has been inherited in a fetus or a newborn, an infant. All right, and the tests are often done on everyone in a group or a whole population. So, for example, here we have the heel prick test, which is testing for a very, very dangerous genetic disorder called phenylketonuria, or PKU. Okay, and that's just so we can begin treatment and management as soon as possible. For example, if we get kids that are born with phenylketonuria in really early on, we can change their diet, and it means that they don't develop the horrible symptoms of PKU. Cystic fibrosis is another example of this. We do have to look at the ethical and social implications of this, okay? And when we're looking at these, we can look at them in 3 different stages, okay? And these are all about when the testing takes place. So the testing might take place post-symptomatic, so after we begin having symptoms. They might take place pre-symptomatic, so before we begin having symptoms. Or they might even take place pre-implantation, so this is before we even think about having the child. Well, no, we're certainly thinking about having the child, but before the sperm and the egg comes together. That's pre-implantation. And these 3 actually dictate the types of implications we're going to look at and the different parties that might be involved. So certainly the first party we'd look at in terms of different implications might be the individual. What are the implications for the individual person? And then we might look at immediate family. Okay, so your parents, your siblings, and then we might even look at extended family. All right, and then we can look at specific communities. And groups. Okay, there might be groups within our community. It might be religious groups, larger groups. And then also we might look at organizations. And religious groups also do fall into organizations, but we can look at bigger organizations in general. So what I mean by this is if we're looking at pre-symptomatic the ethical implications for the individual, all right, they might have an understanding of how to manage a disorder before they actually develop symptoms. But also, do you really want to know you have a certain disorder before you actually develop symptoms? It might actually make change your decisions you have in life, and as some people might think that might not be a good thing. Okay, obviously your immediate family, your parents, do they want to know disorders that you have as a child? Is it going to help them manage anything that you're going to have in the future? Okay. Your extended family, they might start thinking, do we potentially have this genetic disorder? Communities, groups, okay, and then also bigger organizations. We're looking at more economic implications as well. Or in a community, might this person be ostracized because they have a certain genetic disorder? So all of this in genetic information that we collect, we put it together into one of these things, all right? And what is this? This is a pedigree chart. Um, this one looks a bit nuts, but really, as much as it's a crazy amount of information, I never expect you to know all the how to read every single bit of information. A pedigree chart like this is still much the same to a little pedigree chart like this one. Okay. Let's talk about how we can understand a pedigree chart, because at the end of the day, they actually all follow a very similar convention. Okay, the first convention we have to know is that on this side here, we often put the generation. Okay, so for example, here we've got generation 1, and then the little number represents the individual. Okay, so for example, if we were to look over here, this is individual that is in generation 2 and is individual 3. Okay, and that's often how we talk about the individuals. Okay, this is a certain convention that we don't actually always follow. I find though, and I expect you guys to follow this convention because it makes reading these things so much easier. Okay, um, obviously I haven't labeled the last 3 individuals. So 1, 2, 3. We're always going left to right like that. Okay. Sex is also an easy thing to identify. Boys wear squares. Okay, unfortunately. So males are squares. Females, you're all nice and rounded. Okay, that is how I remember it, and it just works for me. Okay, whether an individual is affected or unaffected is also important. So if they're nice and shaded in like this, they are affected, right? If they are like individual 2, 3 that we had highlighted before, they are unaffected. If we are talking about a recessive disorder and recessive disorders only, and we have an individual with a little dot like this, they are a carrier, which means that they are heterozygous, but only for recessive disorders. Because if it was a dominant disorder, this individual would actually be completely shaded in. Okay? And then also we can look at the mating of people and their potential offspring. So a line between 2 people like this means that they are mating. And then if that line has a down line like this and then it goes across, right, this means that these 3 individuals are their offspring. Okay. In addition to this, so these are the things that you need to know from these pedigree charts. In addition to this, if you see things like, for example, like this, it means that these 2 people have split up. If you see these little splits like this, that means that we have twins. Okay. Yeah, and I think that's about it. There are some extra bits of information that we can put into this, but these are the main things for you guys to know. So we need to be able to look at these pedigree charts and actually identify information about what kind of trait we're talking about. So for the first one here, we've got an autosomal dominant trait. And how I know it's an autosomal dominant trait is for a few reasons, okay? The main reason that I would identify this as an autosomal dominant trait is because if we look, we have these 2 individuals that are mating and they have 3 offspring. Their 3 offspring have 2 that have the trait that we're looking at, okay, but 1 that doesn't have the trait that we're looking at. The only way for this to happen and the two that have the trait, one's a male, one's a female, the only way for this to happen is if we had two heterozygous parents that formed two offspring that had at least one dominant allele, so they were A dash each, but then this one actually inherited the two recessive alleles. Okay, that is the main feature of autosomal dominant traits. Okay, so pretty much males and females will be affected equally in a very, very large sample. Here we have a small sample, so we're not seeing that. But all affected individuals have at least one affected parent. We can see that here, where we have one affected parent with one affected individual. Both parents don't need to be affected for that to happen. Okay. Another interesting point of an autosomal dominant trait is that they're often shown that once the trait disappears, it doesn't reappear. So this individual 2-3 that we looked at, he mated with individual 2-4, who was obviously also um, homozygous recessive, all right? And they then obviously had to only have offspring that were homozygous recessive. Okay, so there's our autosomal dominant trait. So the trait would be represented as a big letter in this case. Autosomal recessive trait is the opposite, right? Where the trait is going to be represented by a little letter, all right? And there's a few different things that we can identify as an autosomal recessive trait. So the first thing is, once again, males and females are going to be affected equally in a very large sample. Here's a bad case because the sample's so small. So we have a lot more females affected, but still, in a large sample, we would have equal amounts affected, okay? The most important point about autosomal recessive trait is this that we can see here. We have a female and a male mating, and they have twins, but their twins are both affected, even though they're both unaffected. So how does this happen is that we had two heterozygous parents again that gave their recessive allele to form two homozygous recessive offspring. Okay? Also, we can observe that a trait can skip a generation. We don't see this here, but let's say that individual 3-3 found a nice little mate for himself, all right? And that individual, that mate that he found, was also unaffected, okay? And they had two kids, all right? One child was a female, one child was a male, but their boy that they had was actually affected. Okay, how this happens is, let's say that this female was also heterozygous, this male was also heterozygous, and let's say that they then gave their two recessive alleles to their son. Okay, that's how this happened. That's skipping a generation like that, because we had the trait in that generation, we have it in this generation, but this generation of these two individuals don't have the trait. Okay, sickle cell anemia is a great example of this. Okay, X-linked dominant traits, the next kind of trait, all right, and they're traits that are represented on the X chromosome with a big letter attached to it. Okay, there's a few important features of X-linked dominant traits. Okay, in a very, very large sample, there's actually going to be a lot more affected females than males. All right, and the reason why for this is because females have double the likelihood of inheriting this X big A, and they only need one version, because obviously a female who's affected is going to be X big A, X little a, or X big A, X big A. A male that's affected is either going to be X big A, Y, but they can't be anything else. Okay. But if we do have a male that's actually affected, they have to pass that on to their daughters. And the reason why is because women are XX, the male has to give that X chromosome to his daughters. And that's what's happened here. We have this affected male, all right? And because he's affected, that X big A that he has is passed on to every single one of his daughters. So it's all his daughters, even though their mum is X little a, they're going to inherit the X big A from their dad. Oops, X big A, X little a. So all of them are going to be that. The son, on the other hand, he lucked out because he gets the Y chromosome from dad, and he's going to get the unaffected X chromosome from mum. Okay? On the other hand, if we have an affected or a carrier female, they can potentially pass on the trait to either the son or the daughter. So it's actually not very good to look at affected females like this individual 2-4. So that she's X big A, X little a. And if you look at her offspring, she has one son that's affected. So obviously she passed the X big A to him. All right, but her other son isn't affected, so she must have passed the X little a to him. So there's no actual consistency in that. Okay. And every affected person has to have one parent with the trait. Rett syndrome's a great example of this. All right. X-linked recessive traits, the opposite of X-linked dominant. So we have X little a as our case here. Okay. In this case here, males are actually more likely to be affected. And the reason why is because they only have one X chromosome. So either they have it or they don't. They can't be a carrier. Females, on the other hand, can be a carrier. So a female can only be affected if they're X little a, X little a. A male, on the other hand, can be affected as the X little a, Y. But because they can only inherit that one X chromosome, they're actually more likely to be affected. Okay? If we have a female who's affected, all her sons are going to be affected. So, for example, individual 3-2 here, she's affected. She had one son, he was affected. If she had another son, he had to be affected because she is X little a, X little a. Doesn't matter which X chromosome she gives, her son has to turn out X little a, Y, which is affected. Okay? Fathers, on the other hand, can't actually pass on their trait to their son. So if we look at individual 2-2 here, all right, he had to be X little a, Y because he's affected. And so when he goes to pass that chromosomes onto his son, he can only pass on the Y chromosome from his son, and his son got lucky and got the dominant chromosome from his dad, and so he's not affected. Okay? And also we do notice that we do have some females here that are carriers, and in those cases they would be X big A, X little a. Okay? Red-green color blindness is a great example of this. Then we have the Y-linked trait, which is always nice and easy. So it's just represented on the Y chromosome. We might have a YA, okay, or a YB. It doesn't really matter. Okay, obviously, because we're talking about the Y chromosome, only males are affected, and they're going to be XYB. All right, it's really easy to see these. If you find a pedigree chart where, as you can see here, we've only got males, and it's a nice and big enough, you can almost make the assumption that we've got a Y-linked trait there if it doesn't fit any of the other examples. An example of this is male pattern baldness. All right. Great way to finish the year. Let's have a crack at a year 12 exam question from all the way back when I was in year 9 from 2006. All right. I've given you a handout. Have a crack at this and we're going to go through it together. And that's it. Now we just have to study and get through the rest of it and we are done.